Hi, everyone. I am delegated to welcome you and all today's IEEE Young Professional PS Region 8 webinar and on a topic of great significance and promise fundamentals of solar photovoltaic systems. I'm Ibrahim Al-Muhaysin. It's my honor to serve as the moderator for this engaging session where we will explore the fascinating world of photovoltaics and its potential to revolutionize our energy landscape. As we gather here today, we recognize the growing importance of renewable energy sources in addressing the global challenges of climate change and sustainable development. Photovoltaics, or the conversion of light into electricity, lies at the heart of this transition towards a cleaner and more sustainable future. Our distinguished speakers, Engineer Mira Daher, is highly motivated and result-driven electrical engineer. Uh, uh, electrical engineer with passion for renewable energy and specialization in solar power system, experienced in designing and implementing sustainable energy solutions with a keen interest in power and energy trading. Possessing a master's degree in electrical engineering focused on power and energy trading. Uh, Without further ado, let us extend a warm welcome to our esteemed speaker, Engineer Mira Daher. The floor is yours.
So, hello, Ibrahim, Engineer Ibrahim. Thank you so much for your introduction. I'm very happy today joining you all through this presentation, as it is my very first presentation with IEEE for Young Professionals. So, welcome to this webinar, which is tailored exclusively for professionals like you all who are pioneering the future of clean and sustainable energy solutions. I'm truly delighted to have you join us today, coming together from various corners of the world to engage in a meaningful exchange of knowledge, ideas, and insights that will shape the path of solar technology and its impact on our world. So your presence here really underscores your dedication to the field of solar energy. And it is this passion that propels us all forward towards a brighter and greener future. So before I start, I would like to extend a special thank you to the IEEE Young Professionals section for their unwavering commitment to fostering the growth and development of recent graduates and early mid-career professionals in the ever-evolving tech landscape. And thank you so much again, Engineer Ibrahim, for this opportunity. I'm really happy today. And the reason for this presentation is that a lot of people are really interested nowadays in solar energy. And I would like to give more knowledge, since like 3 to 4 years ago, I had no knowledge in solar energy. So a lot of people nowadays need a boost to start going into this topic or into this domain. So if you can hear me properly, I can start.
Yeah, I can start. Thank you, Engineer Mira. You can start now.
Okay. Okay, so as I've told you before, the title of this presentation is The Fundamentals of Solar PV Systems. I started with something like basic in order to do several webinars later on, as this is my very first presentation. So we'll start with the basics, and in the upcoming presentations, we'll go through more details regarding the solar energy topic, as it is a very wide topic. So in this presentation, I'm going to talk about the types of solar systems in general, what is solar energy, the difference between irradiation and irradiance, a very basic topics that are very important for you all to know if you want to start with solar energy, how a solar module work, the concept of peak sun hours, types of solar modules, the characteristic curve of a solar module, what is the efficiency of a solar module, how to connect solar modules in series and in parallel, and why we connect some in series and others in parallel, the effect of the temperature on solar modules, how a solar system work and the components of a solar system, and of course the types or the main types of solar systems and why we use them and where. Okay, so as we all know, there are two major main types of solar energy. The first type is the thermal systems, and the second type is the photovoltaic systems. So there is a big difference between thermal systems and photovoltaic systems. However, the similarity here is that in the two cases, I'm using the energy from the sun to do something. In the case of thermal systems, I'm using the energy of the sun to heat water through a certain technology. To heat water, for pool heating, for radiant heating, and so on. However, in the case of photovoltaic systems, I'm using the energy or the rays of the suns to convert these rays through electricity and, of course, through the PV module, which is a technology. Okay, so the PV systems produce electricity. These electricity, it can be used to power your appliances at home. These systems can include also batteries where you can store the electricity and use it at night where there is no sun or in critical hours. And of course, other systems don't have batteries, and also you can feed the unused energy that is excess during the day and feed it back into the grid in some places where the grid is available all the time, of course. So what is solar energy? Or in other words, photovoltaic energy. You can hear solar energy and you can hear photovoltaic energy. So when you hear the term photovoltaic is a combination of a Greek word, which is phos, it means light, and voltage, which is named after the Italian physicist Alessandro Volta. So I have phos and voltage, and it gives you photovoltaic. So the solar radiation that comes out of the sun is converted into direct current. This is very important. It is converted into direct current, not alternating current. Okay, so this direct current comes out of the photovoltaic cell. The photovoltaic cell is mainly a semiconductor device. Okay, so solar energy refers to capturing the energy from the sun and converting it into electricity, into direct electricity. Now I have two main words or two main concepts that most of the people are confused with what's the difference between solar irradiance and solar irradiation. So it is very simple. Irradiance that came out of the sun, it is the solar radiation per unit area. So it is measured in watts per meter squared. So this is the curve or the irradiance curve. And the area under this curve is called the solar irradiation. So when I say solar irradiation, you are quantifying, since you are measuring the energy per unit area of incident solar radiation on a surface. And it is measured in watt-hours per meter squared. So when you are measuring the energy per unit area on a certain surface, you are measuring the solar irradiation, which is the area under the curve. And when you are measuring the irradiance, you are measuring the point, which is in watts per meter squared. Okay? So this curve shows the solar irradiation curve, and here you can see at sunrise and at sunset. So solar irradiance increases from sunrise to noon, and it decreases from noon to sunset. Okay, another concept or another very important concept in solar energy is called peak sun hours. And of course, a lot of people are really confused with the concept of peak sun hours. So peak sun hours are not the hours of the day where the sun shines. A peak sun hour is an hour in the day or during the day when the intensity of sunlight reaches an average of 1000 watts per meter square. So when the intensity is not 1000 watts per meter square, you cannot call this hour as a peak sun hour. Okay, so since the peak or the highest solar radiation at sea level is 1 kilowatt per meter squared, or in other words, 1000 watts per meter squared, which is the case when the sun is directly above the clouds, so it is perpendicular to the surface of Earth, the number of peaks and hours is numerically identical to the average solar insolation. And it is showing here in this graph. So this graph shows the solar radiation. So the time from this point till this point is called the peak sun hours time, which is the area under the curve. It is called solar insolation or solar radiation. Let me give you an example. So if a certain location, if I'm telling you that a certain location gets 5 peak sun hours, or in other words, peak sun hours can be expressed in kilowatt hours per meter squared since it is the area under the curve. It means that this area gets 5 hours of solar power when the average intensity of sunlight is 1000 watts per meter squared. So it is very important to know that a peak sun hour is an hour when the intensity of sunlight is 1000 watts per meter squared. So here I'm going to give you another example. So using the example below, you can know how you can calculate the size of your solar system from the peak sun hours. So if I have like a certain location, let me take an example, your home. Your location gives you peaks and hours of 7 peaks and hours during the day. And your home like uses 25,000 kilowatt hours annually. So what you should do is that first you should divide the 25,000 kilowatt hour annually by 365 days to get the kilowatt hour or your energy consumption per day. So when you get your energy consumption per day and divide this energy consumption per day by the peak sun hours per day in your location, you'll get the size or the recommended size of the solar system that you want to install. So here the number is 9.78 kilowatt hours. So you should install a 10 kilowatt solar PV system in this location. I've attached here a photo where it shows the states, where each state in USA has a unique average peaks and hours. So it differs, of course, peaks and hours differs around the world depending on the location. So a small hint that often the number of peaks and hours increase when you are closer to the equator, and generally during the summer month, of course. Here are also examples that I've imported for peaks and hours for different countries throughout the world. I have Italy, I have Japan, I have Texas, I have Alaska. You can see that peaks and hours are higher during summer, and especially during June, July. So you have the highest peaks and hours here. And like it decreases during winter times, like in January, February, December, and so on. This map, I guess most of you have seen this map, which is the solar irradiation around the world. You can see how it changes, how the color changes, how the peaks and hours changes. And as I've told you before, when you are near the equator, you have higher peaks and hours. Now, I'm going to talk also about the solar radiation. We are still in this topic. So solar radiation that comes from the sun and hits your surface or hits the surface of Earth, it is not always absorbed. So you cannot always absorb all the quantity of solar radiation. So this solar radiation can be absorbed, it can be scattered, it can be reflected by components in the atmosphere. So it is not always absorbed. The amount of radiation reaching the Earth is less than what entered the top of the atmosphere. So I have 3 different categories for solar radiation. Solar radiation can be incident directly through Earth, which is called the direct normal irradiance, which is the radiation from the sun that reaches the Earth without any scattering. So you can see it here. This is direct irradiance because it is not scattered anywhere. It is perpendicular to the surface of Earth. You have the other type, which is called the diffuse irradiance. Diffuse irradiance is the radiation that it is scattered by the atmosphere. It may be scattered with clouds, and it arrives in all directions. So it has different directions. So it is not absorbed. You cannot benefit from this type of radiation. And you have the albedo irradiance, which is a combination of direct and diffuse. It may be reflected from soil or nearby surfaces like snow, lakes, and so on. So, in Global Atlas, we provide 3 magnitudes to solar irradiation. The first magnitude is GHI, DNI, and DIF. So, when I tell you GHI, it's a very used, common thing. So GHI is the combination of all the irradiation. So it is the sum of the direct irradiance, the diffuse irradiance, the albedo irradiance, which is a type of diffuse irradiance. So it is the total amount of radiation received from above by a surface, of course, horizontal to the ground, and it is measured in kilowatt hour per meter squared. So in other words, GHI, which is the global, from its name, it is the global. It includes both the normal and the direct and the diffuse irradiance. And this also shows you the direct irradiance that comes to your solar panel, the reflected one. This one is diffused due to atmospheric scattering, and so on. Okay, so we've talked generally before about the working of a solar panel. However, now we're going to go through details of how a solar module works. So, as we all know, a solar module is made up of solar cells. Solar cells are interconnected together in series in order to give you a solar panel. I'm going to show you the composition in an upcoming slide. So, let me give you an example with this picture. So you have the solar panel. So every solar cell have 2 layers. The first layer is called the N-type, as shown here, and the lower layer is called the P-type. It is an N-type of silicon, and here I have P-type of silicon. So before, every solar module is mainly made up of silicon. Okay, so it is a semiconductor material. It has a N-type of silicon and a P-type of silicon. The surface between these 2 layers, which is shown here, it is called the junction. It is the P-N junction, which is the surface between the P-type and the N-type layer. When the light that comes from the sunlight, in other words, the light is called the photons. When these photons strike the surface of a solar panel, energy from these photons frees the electrons. So, due to the opposite charges between N and P, the electrons want to flow from the N to the P because it is from positive to negative. So, but the electric field at the P-N junction prevents this from happening. So, when you connect a circuit outwards between the positive and the negative, or the presence of an external circuit provides the necessary path for the electrons in the N-type layer to travel to the P-type layer. So here you have a circuit that travels from the N-type to the P-type layer, as shown here. So from the red in positive and the black in negative. So the electrons flowing will provide you electricity and you can light your load. Okay. So now I'm going to talk deeply about the composition of a photovoltaic module. So as you can see, these are the layers of a photovoltaic module. It's not a single material. It is made up of different layers. So the first layer is called the aluminum frame. The second layer is the glass. The third layer is encapsulant material. It is called EVA. You have the solar cell, another encapsulant material, a backsheet, and at the end you have the junction box. So What is the aluminum frame? So the aluminum frame plays a very critical role by protecting the edge of the laminate section. It protects the edges. The aluminum frame protects the edges of the laminate section, housing the cells. So it houses the cells and provides a solid structure to mount the solar panel in position. The second one, which is the front glass sheet protects the PV cells. So it is very important to protect the PV cells from the weather and impact from hail or airborne debris. So the glass is typically high tempered or high strength, have a high strength tempered glass. It has like 3 to 4 millimeter thick, and it is designed to resist mechanical loads and extreme temperature changes. So the glass is very important. The encapsulant material, so it is called EVA. So EVA stands for ethylene vinyl acetate. So it is the EVA material. It is specially designed polymer. It is highly transparent. It is highly transparent plastic. It is used to encapsulate the cells and hold them in position during manufacturing. So the EVA material must be extremely durable and tolerant to extreme temperatures and humidity. So it plays a very important part in the long-term performance by preventing moisture and dirt ingress. Now you have your solar cell. As we all know, the solar photovoltaic cells convert sunlight directly into DC electrical energy. The performance of the solar cells are determined by the type of the cell that we'll talk about, all the type and the characteristics of silicon, which has two types we're going to talk about. I have the monocrystalline silicon and the polycrystalline silicon. You have also the backsheet. The backsheet is the one shown here. So the backsheet is the rearmost layer of standard solar panel. It acts as a moisture barrier, okay, and it is the final external skin to provide the mechanical protection and electrical insulation. And you have lastly the junction box as shown here. So the junction box, it is a small waterproof enclosure located on the rear side of the panel. It's located here. So it is needed to securely attach the cable that are required to interconnect the panels. So this junction has a positive side and has a negative side, and it is used to connect the solar panels together. Okay, so I'll drink and get back to you. So, as I've told you before, the solar panel is made up of different solar cells that are connected together. When these solar cells are actually connected together, it gives you a solar module. Once different solar modules are connected in series or in parallel, it is then called solar array. So this is the shape of a cell, of a certain solar cell. This is the solar module, and this is the solar array. So the composition of a photovoltaic module. So I've told you before that a solar module is made up of different cells that are connected together. So the voltage of individual solar cell ranges between 0.5 to 0.6 volts. So each cell of these cells, as you can see these cells that are connected, each one of these cells gives you a voltage between 0.5 and 0.6. Traditional full solar panels, we call them full solar panels because the solar panel is full, it is not cut in half. So traditional solar panels have number of cells that are between 60 to 72 cells connected in series. However, the half cells have nowadays 120 or like 144 cells, which have lower resistance, and it means like you have more energy and you can capture more energy and produce more energy. So to reach higher voltages, many cells should be connected together to give you solar modules. So when solar cells are connected together, they gives you a higher voltage. To reach a higher voltage and current, of course, many cells should be connected in a combination of parallel and series. Here, I'll give you an example of a data sheet. I've took a screenshot from the Jinko Solar PV module data sheet. So here is the Jinko Solar. It gives you some mechanical characteristics. So it shows you, the data sheet shows you the number of cells. So here we have 144 cells. Okay, these are the dimensions, the weight, the front glass dimensions, the frame, the junction box. It is IP68 rated, and so on. And this is the composition of a solar module. Here you have the number of cells that are connected, and at the end you have the negative and the positive. Since, as I've told you before, a solar module gives you direct electricity, direct current. So we'll know in the upcoming slide how we can convert this direct current from direct to alternating to power your appliances. Types of solar panels. So you can see here in the data sheet, you have the P-type monocrystalline. So this is meant by a type of a solar module. So I have three different main types of solar modules that you all heard about, of course. It's very popular. You have the polycrystalline solar panel, you have the monocrystalline solar panels, and you have the thin film. What's the difference between these solar modules? So first of all, polycrystalline are the first, they are the most traditional solar panels. They were the very first types of solar cells to be developed at the beginning of this industry. However, they are still used nowadays. Polycrystalline modules are made from different silicon crystals that are melted together, and in order to give you the most efficient option. However, they have a lower cost, but their lower cost comes, of course, with less efficiency and a moderate lifespan. So they have a lower lifespan than the monocrystalline solar modules. The monocrystalline solar panels, as their name suggests, these are single crystal modules. So they are made of a single crystal. They are made of one pure silicon crystal. So we don't have several crystals. They are made of only one pure silicon crystal. That's why we call them monocrystalline solar panels. Okay, this makes them the most efficient crystalline solar panels in terms of their energy conversion. So monocrystalline solar panels also have the highest performance. So they have the highest performance of solar panels, and they have the longest lifespan. But also, of course, this comes with a higher price tag. Now, the thin films, they are not very popular, not very used a lot. Okay, they are flexible. Okay, so these solar panels are composed of very thin layers. So they have a very thin layer. As a result, it can be flexible. However, they have the shortest lifespan between monocrystalline and polycrystalline. I wanted to show you the most the technologies, the most recent technologies in solar modules with their efficiencies. So the most recent solar module is the N-type top cone and N-type HJT. So these are half-cut modules, of course. They have an efficiencies that range between 21 to 22.5%. And you have the N-type HJT has reached the 23%, and the N-type back contact is reaching the 24% efficiency, which is a very good and high number. So solar energy technology is becoming better and better every year because of the lot of research. So here I've shown you two different data sheets of the same solar module of the same brand, which is Jinko Solar brand. I can show you this module is a datasheet for the polycrystalline PV module. This is one for the monocrystalline or the P-type and the N-type. You can see different efficiencies. So here I have lower efficiencies, here I have higher efficiencies. So you may hear, of course, with the concept of STC and NOCT. What is STC and what is NOCT? STC stands for standard test conditions. So what are standard test conditions? So the laboratories or the manufacturer have given this name or standard test conditions in order to let you compare between solar modules. So you may hear that this solar module is like Jinko solar module. It is like rated 500 watts at STC conditions. What does that mean? Another module is also rated 400 watt peak at STC conditions. So in order to compare different modules, they came out with a set of criteria that they test a solar module at in order to compare these different solar modules together. The criteria is solar cells are all measured or are all tested at a cell temperature of 25 degrees Celsius. They are tested at a light intensity of 1000 watts per meter squared, and the atmospheric density is 1.5, which is the sun's angle directly perpendicular to the solar panel at 500 feet above sea level. So this is what is meant by STC conditions. However, what is meant by NOCT conditions? So NOCT conditions are another review of testing the solar module. But now what I'm doing is that I'm testing a solar module on a more realistic view. What is meant by this? So the sun is not always shining at 1000 watts per meter squared. The temperature is not always 25 degrees Celsius. The air mass ratio is not always 1.5. So NOCT is another realistic measure. It is called the normal operating cell temperature. So it gives you, or it measures, or it tests the modules at a solar intensity of 800 watts per meter squared, which is closer to mostly sunny day with scattered cloud, and at a temperature of 20 instead of 25, and so on. So this rating will be lower than STC. So of course, a module that is rated or tested at STC should have a higher wattage than a module tested at an OCT. So this is an example of a solar module. It is also from Jinko Solar. So you can see here that this is the module type. So you can see this data sheet. So I've taken a screenshot of a certain data sheet. So this module, or this type of module, ranges from 530 till 550. So you have from this model 550, 535, 540, 545, and 550. So you can see here that each module is tested under STC and NOCT conditions. So the 530 modules at STC condition is rated like 530 watt peak. However, at NOCT it is 394. So it can show you that the wattage decreases from STC till NOCT. Okay, so a module that is rated, for example, 550 at STC, it is 409 at NOCT. Of course, and it shows you in the data sheet how they test at STC and NOCT. What are the conditions? So these are the conditions that I've already told you. Okay. So this is the characteristic curve of a solar PV module. So this is a very important curve that all of us, the ones that studies electrical engineering or renewable energy engineering at the university, have studied this curve. So this is the solar IV characteristic curve. So it shows you the IV, which is the current versus the voltage, and it shows you the power versus the voltage. So the current voltage characteristic of a typical silicon PV cell operating under normal conditions, it shows you the power delivered by a single solar cell or panel, which is the product of the current and the voltage together. So if you multiply the voltage and the current, or each voltage and the current, you'll get here what this graph is, the PV graph. So this point where you are having the maximum voltage and the maximum current gives you, of course, the maximum power, which is called the maximum power IMP. This point is called the short circuit current. This point is called the open circuit voltage. So what's the difference between solar or open circuit voltage and I short circuit current? So open circuit voltage, it is when you have a solar module, you are measuring the output of this solar module at no load, you will get the open circuit voltage. If you put the positive and the negative of a certain solar module, you'll get the I short circuit current. So the goal here is that you should take the highest current out of the solar module, which is the nearest to I short circuit, but not I short circuit, and the voltage or the nearest voltage point to V open circuit, which is VMP and not VOC. So the point which gives IMP times VMP is called PMP. PMP is very important since it gives you the highest power that comes out of a certain module. So I've shown you before here that every solar module have a VMP and IMP. So when you multiply VMP by IMP, you are getting the highest power that came out of a certain module. And also you can see the VOC, which is the open circuit voltage and the I short circuit current. It is also the open circuit voltage and the I short circuit as shown in this graph here. Okay. Of course, you all heard about the solar panel efficiency. It is very important, and you can calculate the efficiency of any solar panel using this formula. Okay, so the solar panel efficiency is also measured under standard test conditions. It is based on a cell operating at a temperature of 25 degrees Celsius. You have an IR radiance of 1000 watts per meter squared and an air mass ratio, which is 1.5. So when I tell you the efficiency of a panel, what does it mean? The efficiency of a solar panel, it is calculated by dividing the maximum power or Pmax at STC, which can you get from the datasheet of a PV module. So you can get the maximum power, which is Pmax, which is like here. It is for the 575 panels, 575. For the 555, it is 555. So you divide Pmax divided by the area. What is the area? The area, it is for a solar module. You multiply the length by the width, and you multiply it by 1000 watts per meter squared, since you are testing or you are getting the efficiency at standard test conditions, and you multiply by 100 in order to get the efficiency of a solar module. If you do this calculation, you get the efficiency stated here, since this is the module efficiency at STC. So it differs for each type of solar module, for each rating, and for each size, of course. The effect of temperature on solar PV modules. So what is the effect of temperature on solar PV modules? The graph here shows you the effect of temperature on solar PV modules. Okay, so here you have the current and you have the voltage. This is the characteristic curve of the PV module. Let me start with the temperature. It is very important for you to know the effect of the temperature when you want to design solar PV modules or solar PV systems in general. So first of all, this is a calculation. At T equals 0 degrees Celsius, T25 at standard test conditions, and at 50. So I'm increasing the temperature from 0 to 50. At 0, you can see that the voltage increasing, the open circuit voltage increases. At STC, it is in blue. At 50, the voltage decreases. So it shows you also that increasing temperature increases the current. However, it slightly increases the current. In case of the voltage, when you decrease the temperature, the voltage increases a lot. So this is very important when you want to design different solar modules that are connected in series. You want to take into account the temperature, since if the temperature in this location decreases a lot, you have to take into consideration that the voltage of this panel will increase also by a certain percentage. And when this voltage increases, you may affect the input of the inverter that takes the solar modules. So you have to check for this point. However, concerning, and in other words, when you increase the temperature, the power also, the output power will reduce. Okay, so now we are changing the irradiance. Okay, so it shows you that when you increase the irradiance from 250 to 1000, or when you decrease the irradiance from 1000 to 250, so what happens here? It shows you that the current changes a lot. However, the voltage will changes a little with the irradiance. So current increases with constant irradiance and VOC changes little with irradiance. So in other words, the maximum power increases with increasing irradiance and the maximum power voltage changes a little with irradiance. Here is another graph. It is like calculated. I've done this calculation for like JA solar PV module. This module is rated at 550 watt peak. So you can see here that at T equal 10, 25, 40, 55, and 70, it shows you that the maximum power of the module drastically changes. So at 10 degrees Celsius, the PV module is 580. At 70, it is 467.5. So it decreases a lot. And also it shows you here the watt or the maximum power of a module with changing irradiance. So at irradiance of 200, the wattage of the panel is 105, which is very lower than the incident when the incident irradiance is 1000. The connections of solar modules. So this is very simple. So when you want to design solar PV modules, you want to know when to connect these solar modules. So when you do series connection, the voltage of the solar modules increases since you are connecting the modules in series. So you are adding the voltage of these solar PV modules. How you connect solar modules in series? So to achieve this, you connect the negative terminal of one module to the positive terminal of the other module as shown here. So positive to negative, then you have a series connection between panels. So if you want to connect panels in parallel, so when you connect panels in parallel, and according to physics, it is so you are then adding the current between these solar PV modules. So the voltage in the parallel combination of modules remain the same, okay, because you are connecting them in parallel as that of the individual voltage of a module. Okay, so the parallel combination is achieved by connecting the positive terminal. Okay, so the positive terminal of one module to the positive terminals of the next module, and the negative terminal to the negative terminals of the other modules, and then you'll be connecting panels in parallel as shown in this figure. Of course, you can also connect panels in series parallel connections. So as shown here, these two modules are connected in series, these two modules are connected in series, these two modules are connected in parallel with these two modules. So this is very important because when you want to design a solar PV module, you have to know how I want to connect the PV modules. I want to connect them in series and parallel. Am I able to add the voltage? Am I able to add the current? This depends on the input of each inverter that you're using. So it is very important to know, till now, I've not talked about the complete system of a solar PV module. I've talked about only the solar module alone, the solar module in general, in other words. So each solar system is made up of solar modules. So as I've told you, the solar modules gives you electricity, direct electricity, which is direct current. So I cannot power most of my appliances using direct power. So I have to use something or important something in order to convert this direct current to alternating current. So this is done by the use of an inverter. So the use of an inverter, the inverter is used in order to convert the direct current into alternating current. So most of the inverters nowadays have an embedded charge controller inside them. So you may have also inside your system batteries. Okay, so these batteries are used in order to to store the energy inside them. So you can store the energy in order to use them later at night, for example, in order to power your load, and you can have an optional generator connected also to your systems. So we have several types of PV systems. The very first type, which is very popular is the grid connected system. So from its name, it is called grid connected system. It is the on-grid system. Each on-grid system, it is connected to the utility grid. This system would work only if the grid is available. So if the grid is not available, these systems cannot work. Okay, so in like countries where the grid is not available, like in Lebanon, for example, the grid is very intermittent, so we cannot use the on-grid systems because the grid comes like 2 to 3 hours a day. So these systems are made up of solar modules, a solar inverter, we have a net meter here, that because you are able to send power to the utility and take power from the utility, it has a bidirectional operation. So a grid is of course required in these systems, since the inverters need to be provided a reference voltage and the inverter needs to sync with the grid in order to export energy back to the grids. So on-grid systems make sense for locations with no daytime power cut. Of course, many countries that don't have a power cut, or with less than like 2 hours of daytime power cut. So these types of systems reduces your electricity bills, of course, since it is cheaper than implementing a battery inside your systems, and there is no recurring cost of replacement components. So you don't replace the batteries after 2 years, 3 years, or 5 years. So here you have, of course, in this system, you have a bidirectional meter between the traditional and, of course, there is a very difference between the traditional meter and the bidirectional meter. So traditionally, you have a meter that measures the energy that goes to the grid. So the difference between the traditional and the bidirectional meter is that the unidirectional meter only displays the total energy imported from the grid, the total energy that you import. However, as you can see here, this meter is a bidirectional meter. It records 3 readings, which is the total amount of energy exported, the total amount of energy imported, and the net energy difference between the export and the import, in order to know how much you're going to pay at the end of the year, for example. Okay, so here I've talked everything about. So this is the working mechanism in general of on-grid system. So once solar generation starts during the day, this generated energy is firstly consumed by the load. Okay, so I have priority to consume this energy or to give it to the load. So once the load requirement is satisfied, so you are satisfied with this PV generation, the remaining will be then exported to the grid. So you allow export of energy to the grid. The grid by itself acts as a virtual battery, taking in all the excess energy that has been exported. During the night, which is also important, when there is no solar, the loads can import the banked energy. So I'm using the grid as a battery. Similarly, when there is less generation from solar due to the cloudy conditions, the required energy is also imported from the grid. So at the end of every billing cycle, the export and import billing will be calculated, and this net will be calculated with the help of a bidirectional meter, of course. The second type of systems that we are mainly using in Lebanon, because as I've told you, we have intermittent grid in Lebanon. So it is simply the standalone PV system. So these systems feature batteries. They are not connected to the grid. The automatic solar system produces electrical power to charge the batteries during the day in order to use them during the night when the sun is not available. Most standalone systems are small-scale systems. They employ rechargeable batteries to store the electric energy supplied by a PV array. And it is shown here. Now I'm going to talk about hybrid PV systems. So what do we mean when we told you hybrid PV systems? So what's the case? Some people are interested in solar power or solar power towards the idea of being completely removed from the grid. This is what's called the on-grid. However, remaining connected to the grid and investing in a battery backup system will actually provide, of course, more benefits. What is meant by a hybrid system? So a hybrid system is when your solar panels remain connected to the grid, so they are still connected to your grid power lines, and have a backup battery to store excess power also. So how does it work? The sun rays are absorbed by solar panels. It goes through the inverter, of course, the direct current, it goes through the inverter to create usable electricity. From there, electricity either goes to your home, so either it satisfies your load, or of course to your battery, or to the grid. So you have three options here. So the benefit of a hybrid system is that you will always have power in every situation. And with a backup battery, the excess energy that your solar panels create will be stored, of course, in this battery. Then, when the sun is not shining, this battery will provide your power during the night, system blackouts, or during system blackouts, or inclement weather. So, with a hybrid system, if you were to use up all the power in your battery, you have the ability to draw power from your electrical grid, of course. So, you have three different options, which is a safer decision. Now I like to end my presentation with like some results that I've drawn from several reports that are posted online. You can say that solar PV still dominates renewable energy capacity additions. Solar PV installed power capacity surpasses the coal by 227, becoming the largest in the world. Solar PV generation increased by a record of 270 terawatt hour, which is 26% in 2022, and it reaches like almost 1,300 terawatt hour. It demonstrates the largest absolute generation growth of all renewable energy technologies in 2022, surpassing wind for the first time in the history. And also, the cumulative solar PV capacity almost triples in this forecast, growing by almost 1,500 gigawatts over the period, exceeding natural gas by 2026 and coal by 2027, which is very interesting. You can see how solar energy is actually growing, and this is like very, very interesting. So, as a conclusion, you can say that solar energy is a reliable form of energy. So, solar systems are becoming very affordable and accessible due to the global energy crisis over the past few years. Um, uh, Solar PV system requires a very little amount of maintenance. A solar rooftop system is long lasting, so it gives you a beautiful and blend into your environment. So also it definitely, of course, helps us tackle global climate changes by reducing the carbon footprint and waste. I would like to thank you all for joining today's webinar. I'm very happy I gave you this webinar today, as it was my very first webinar with IEEE. Thank you so much for watching, and stay tuned for upcoming presentations that I'm going to give you about the or related like to the design, to the types of systems in details, how to design PV systems. Stay tuned at PES LinkedIn and YouTube account, and I'll always post new webinars on my page on LinkedIn. Thank you, everyone.
Thank you, Engineer Mira, for your insightful and engaging presentation, your expertise, passion, and throughout research made the topic accessible and informative. Your engagement, speaking style kept us to captive throughout. We appreciate your valuable contribution to our event and look forward to learn from you in the future, inshallah. Thank
Thank you
you,
so much.
Engineer. Thank you, Engineer Mira. You
Thank you.
can, Engineer Mira, take us 5 minutes to get some Q&E from
Okay,
the participant.
of course.
There is one questions from Fish Power. Doesn't mm, peak sun hour depend on inverter sizing ratio? Hence, the 1001 watt per meter square number.
Okay, so as I've told you before, no, it is not dependent on the inverter. Can you please repeat the question? It is related to the inverter what?
Depend on inverter sizing ratio.
No, it is not dependent. So what depends on sizing the inverter is the scale or the size of your system. Okay.
Thank you. Anyone to want to ask?
I've mentioned also that peak sun hours are actually related to the size of your PV system. And when you get the size of your PV system, you can then size your inverter, of course.
Okay.
Okay. Can I please ask the audience, where are you watching us from?
Please write your place.
And how you found the presentation too. And also, I just want to hear some recommendations of upcoming webinars, what you are interested to know more about, what are the topics that you are interested in.
It's from Canada, from Palestine, UK,
Wow.
Seattle, USA, Turkey, Lebanon, Indonesia, Armenia.
Oh, wow. Okay, so I would like to ask you, how was the presentation? Did you found it helpful for you guys? Is it your first time, or are you still studying at the university? Are you working in the solar field? What are your interests in the future? Would you like to know more about solar energy? Ideas about the second webinar? I've previously did a webinar with IEEE Lebanese American University in Lebanon. It was related to sizing PV systems or designing PV systems using the PV software. We can also do a webinar related to this one. What do you think? Are you familiar with the PV software for simulating PV systems?
A lot of participate. Thanks for your materials and presentation. Thank you, Mira.
Thank you so much, guys.
A lot of participate. Thanks for you. There is one questions ask about choosing between solar panel manufacturers. How I would like to know more about choosing between solar panel manufacturers.
Okay, so there are a lot of solar panel manufacturers nowadays, and most of them are like Chinese solar manufacturers. So you should make sure that your solar panel is a tier one solar panel. Okay, you should make sure that a lot of people are installing out of the solar module. You should take a warranty letter for your solar module. You should ask your manufacturer, of course. You should make sure of their manufacturing process. um, what are the certifications of this solar module? So you can ask for a lot of things. According to my experience, the most used solar panels nowadays are like Longi Solar, Jinko Solar, Canadian Solar, Trina Solar. You can write them down if you want to search for them. You can also search for JA Solar. It is mainly used also. Um,
This another one, Wajih, ask about more deep dive into the design process would be great in the
yes,
future,
of course.
inshallah.
Yes, yes, of course, Waji. I started with a very basic presentations for people who are still starting to know more about solar energy, who are interested, who want to know more if they want to start working with solar energy. So the second presentations will be like more advanced presentations diving into the deep design of each types of systems. So I'll start with on-grid systems, off-grid systems, and then into hybrid systems, how we accurately design these systems.
We appreciate that,
Thank you
Engineer
so
Mira.
much.
And now we close the event, and ladies and gentlemen, we have reached the end of our enlightening webinar on solar photovoltaic fundamentals. I extend my heartfelt gratitude to our distinguished speaker, Engineer Mira Daher, for sharing their invaluable insight and knowledge with us. Their expertise has undoubtedly deepened our understanding of the principle and applications of photovoltaics. I would like also to express my appreciation for all participants on behalf of the organizing team. I extend my sincere thanks to each and every one of you for your presence and participation. Thank you once again and wish you all continued success in your endeavors to create more knowledge about these valuable topics. Goodbye and take care.
Bye, everyone. Thank you.
Thank you. Thank you.